So some other people join, so I guess I can make a quick introduction about myself and Javier, and a quick kickstart, set the content and the objective of this short webinar. So first of all, my name is Filippo. I work in ARM research in the software large-scale group system. Javier is a colleague of mine, working as well in the software large-scale group system. I know several of you are more like an HPC hub type of person. Javier comes with a computational background, but he's been also involved in the enablement and working on Gem5 simulator. This webinar has been organized by, essentially the initial idea was in the context of MaX, but not everybody here is a MaX person. But we wanted to promote this webinar as a way to educate and share it with the MaX partner and anyone interested in co-design for the next generation of systems. What we do in ARM around some of our key technologies, some of the key tooling that we use both for simulate and emulate current and next generation instruction set. So in MaX, ARM Research has a role in the work package 4, that is the co-design. And this webinar and the one that's going to be on Thursday, and if there is a need of follow-up, those one in the future, we'll address the need of how we actually do co-design and what kind of insight we can gather by looking at workloads and understanding how to behave with the currently and the next generation system. So I will let Javier going through the entire presentation. I will have to step down and go to something else. Javier is going to talk about SVE, what SVE is, what are the good things about SVE, why we came out with SVE. We will introduce the Gem5 simulator, which is the tool that mostly research is using to do this design exploration for SoC design. Javier already mentioned that this presentation is based on a content that comes from a much larger deck. So the objective of this meeting is really give you a flavor of what is what and what we use this tool for. It's not a full tutorial because it will require much more time. But if there is interest and there is willingness to learn, because we need it's a tool, but tool require tweaking and tuning and understanding how it works, then we can follow up and organize a more in-depth series, or maybe a face-to-face event inviting MaX people and other series and go more in-depth into the topic. So without further ado, I'll leave Javier explaining and starting the presentation. And the time is around 1 hour. Hopefully, we're also going to record it. So finger crossed. But if something goes wrong, we will be able to repeat it. So Javier,
thank you, Filippo. So as Filippo was saying, this talk is going to be first about ARM SVE, which is ARM's bet for HPC and HPC or large-scale systems in general. And a second part is going to be about Gem5, which is a simulator we use here internally in research, and that we promote externally also for partners if they want to do some architecture exploration or evaluation, that sort of thing. It's not going to be an in-depth talk, mostly because we don't have the time. Just like a proper overview of SVE would take slightly over an hour. So I will just give you a hint of what it is, and to make sure that at least whenever you hear something about SVE, you know what people are talking about. And same with Gem5, I won't give you a tutorial step-by-step how to run, how to analyze the results and generate traces, all those sort of things. There's plenty of documentation online if you want to follow tutorials for that. But I wanted to give you an overview, so at least you know first what kind of simulator environment is Gem5, potentially what you can accomplish with it, and so terminology is not completely foreign to you, because I assume that most of you are not architects, if any at all. So it's not going to be a talk about architecture, hopefully. Feel free to interrupt me. If you see that I'm rushing for whatever reason, just don't hesitate, just interrupt me, and I will try to slow down. All right, so with that, about SVE, so the first question is a small introduction to vectorization. The classic vectorization is, you'll see something like this, a function that takes a couple of vectors and outputs another vector. This one is just doing the addition of two vectors, vector B and C, and add that, store that in vector A. The first step usually in vectorization is you unroll your loop. Depending on the length of your vector, in this case, if you have a vector length of 4, like most SIMD extensions nowadays for well, it depends on the version, but generally speaking, if you have 64-bit operands, you will have an extension of 4 of those at the same time. So this is what you would do. And roll 4 times, and then replace those 4 operations. Well, first, if your vector is not a multiple of 4, you will need to add a loop. And also some extensions might require you to add, besides the epilogue to the loop, you'll have to add on top of that the prologue if you have to align your accesses for whatever reason. I think most extensions nowadays work around that, but that still might be something to consider. In something like Neon, you just replace your load operations for vector loads. So it will load several, like four elements at a time. And I don't know if you can see the arrow, the cursor, but okay. You will load the 4 vectors, vector B, vector C, and then you will just add vector B and vector C into vector A, and you have the result, and then you can just store it in whatever memory address you have to. And then you still have to do sequentially your loop tail. When you go into the details of the assembler, the code generated by the compiler, you'll get effectively just the same thing. You can see here you have the loads and the stores. Your loop tail is here, and it's the same thing, just load, add, store, and then that's the loop variable. Just add 4, jump if you still have some elements to process, and repeat. And same for the tail, but this code is sequential. You can tell because here you have Q vectors, which are Q registers, which are vector registers for Neon, and W register, which are integer registers, like standard ARM registers. So just for reference, you can see in X0 we will be passing A, in X1 B, in X2 C. Don't get too scared. This is just for reference. It doesn't matter if you don't quite follow this yet. It's going to be way more pictures in the future. So in Neon, you're working with 128-bit vectors, which is very limited for HPC standards. Also, it doesn't support conditional execution. So if there is, for any reason, you have any sort of flow control within your loop, like if statements, that you cannot vectorize that. That's quite limited nowadays, especially with HPC workloads. This used to be enough for multimedia processing, which is the reason Neon was designed. That's the area of design for these extensions. Also cannot operate with non-contiguous memory positions. This is something that's, well, it's inconvenient more than anything else, but it's another point that will make Neon well, less suitable for HPC. So one might wonder, should we then create a newer Neon extension? I think actually Neon 2 was created for ARM v8, ARM v7, sorry, it included like some sort of floating point extension, whatever. But then what happens with that's not enough? You need like wider vector extensions, then you have to create Neon 3. And then what happens if you have a partner that wants to implement Neon 3 but not Neon 1? Do you force them to implement everything? And then all of a sudden you need a new one, and you keep using your your space for new instructions. ARM is not like Intel. Intel has different lengths for their instructions. They have instructions as short as 1 byte or 2 bytes, and then they can go up to 6, 7, whatever. They don't have that problem. They don't have problems with that. We do have a very limited naming space for our instructions. It's 32 bits, so we cannot just keep adding extensions on top of extensions. So this is what we came up with, which is again the problems. Different partners have different vectorization needs. If you are going to implement a processor for a mobile phone, you probably don't need 512 bits for your SIMD unit. Maybe 128 to do some signal processing is more than enough. Also, the ISA namespace is limited, as I was saying. So we cannot just keep adding more extensions and more extensions. We need something that's flexible enough to account for your standard growth, which is adding bits to your SIMD. Also, if you have your code vectorized for one extension, but you're running a processor that doesn't have that specific version or has a newer version, well, it's costly. That's more development time. You have to control what's running on what. You lose compatibility. That's a problem for an ecosystem like the ARM ecosystem, where effectively every manufacturer does their own thing as long as they respect the same ISA, right? And lastly, but not least, is the SIMD instructions. The classic SIMD, they are designed with media processing in mind, not HPC. So the solution from our side was create scalable vector extensions, so partners can license the vector length that suits them best. It has to be in increments of 128 bits, so it can be 128, 256, 384, 512, all the way up to 2048. All of those are valid vector lengths for our extension. And then we introduced this concept of vector length agnostic programming. We are going to vectorize our code, but the resulting source code is not going to depend on the specific vector length. You could potentially do that, but then your code won't be portable anymore. Also note that just because the code is portable, that doesn't mean that performance will be portable. Even if it runs, and it will run, maybe you can tweak it to make it work better for wider vector lengths, but those are fine-tuning problems, so that's fine. Also, this extension is HPC focused, so you will see more instructions dedicated to ease the work of the compiler when it has to do automatic vectorization. You will see instructions that that don't make sense in your typical media processing workloads, but that can accelerate classic HPC workloads. The basics of the architecture, we add a bunch of registers effectively. You have your data registers, of course. They overlap with all the other registers in the system, the integer registers, the neon registers, the floating point registers. And then the length will depend, obviously, on the specifics of the extension. We added 32 of them, so that's a lot. You can potentially not only vectorize, you could even unroll your vectorized loops to even push more operations into your pipelines if you want. Something more exotic that we added is the predicate registers. These are just controlling conditional execution, so you could potentially just fill your vector with data, but operate only on a few of them, or then you can invert the bits of your predicate register and operate on the other half. That's just your normal conditional execution. This is more like the original classic gray vector extensions. And then there's this special register, which is the first faulting register. Is that one that you can see up here. I don't think we'll have time to get into details about this, but this is something quite special that we added that solves potentially some problems with structures with unknown length. So what do we offer? Well, data types, all your integers, 8, 16, 32, 64 bits, floating point single and double precision, and for some operations, we also add half precision. This is one of those things that might not make a lot of sense, but it turns out that if you're running machine learning and neural network training, that's exactly what you want, half precision, so that the extension includes that. For memory operations, you can do contiguous loads and stores. As always, we also added the operations to load structures. So these operations will do the automatic rearrangement of data from an array of structures to a structure of arrays, which is the way that you can vectorize operations on structs. So if you have your usual RGB or XYZ structure representing a color or a pixel, and then you can rearrange it in a structure that has one array with all the X, another one with all the Ys, another one with all the Zs. You can do that in a vector way with those instructions. Then you have the non-contiguous loads and stores, also known as gather-scatter, and also stride loads if you want. You can do that. Another of the special operations we added is non-temporal accesses. We added the possibility for the memory subsystem to understand special load requests that won't be cached. So if you're doing any kind of a stream operation and you don't want that to be cached, because this was going to be like read one, use one, you don't want to involve the whole cache hierarchy in there because it will mess with all the other processes. You are not getting anything out of it anyway. So we provide non-temporal accesses. We also added speculative accesses. That's what the first faulting register is for. That will allow you to, in certain circumstances, access, not access, but speculatively access outside of your memory boundaries without triggering a fault. Your classic load and replicate, those are basic. And as arithmetic and logic operations, you have all your classics. We obviously added reductions, very important for matrix multiply and those sort of things, and convolutions. We also have some exotic instructions, for instance, population count, an instruction that will give you the number of set bits in an element. We added predicate-specific instructions to generate predicates, manipulate them, partition vectors using the predicates, all those sort of things, and permutation operations, ways to extract elements from the vector, compact your vector, just shuffle things around, all very useful and interesting for data processing. Now, if we go back to our neon vectorization, we can see this is your code. Is quite lengthy. You have your vector section, the non-vector section, and now we look into the vector length agnostic version of that for SVE. We've lost all the tail of our loop, and we are effectively left with just the vector part. There are a couple of instructions here that I'd like to explain how they work. This is as far as and deep as we're going to go into the specific of the extension. I don't think there's any, if we have time left at the end, I also have a few slides prepared explaining how things like the first faulting register work, but I don't think it's wise to get into it right now. But just so you have an idea of how all of this works, if you have your destination register, I think A was the destination, yes. B is one of your sources, C is the other one, and then in X3 we will find N, and X4 is going to be our I, the loop variable, that we will set at 0, and we will branch to test the condition first, and here we go. This is the first instruction. This is a specific SVE instruction. Is one of the predicate manipulation instructions. Is while instruction. Is not exactly like a while loop. This thing is going to initialize the bits of a predicate register to 1 for as long as a certain condition, in this case, less than, well, it's a given. It's true. So as long as x4 is less than x3 for all the elements of the vector, or for each element of the vector, it will set to true or false. This is effectively the description. So if we see what's going to happen, here we have x4 is going to be our index, which is going to start at 0. Then x3 is going to be the length of the vector, which is going to be 20. So what this thing is going to test is if x4 is less than x3, x4 plus 1 is less than x3, 2, 3, 4, so on and so forth, until the last element of your vector. And this here, I set it in a way that you can fit 16 elements in a vector, but realize that it could be just half this, and you could still use this. So what will happen is, this is true for all of them, because 0 plus 15 is still less than 20, so that's still true. So all of them will be set to true. So when you go back here, this branch instruction, what it tests is if the first element of the vector is still true. In this case, this one, and it is still true, so it will branch. Back here, it will load starting from x4, which is your index, one source element, the other source element. It will add them together, and then it will store them back in the destination register. This is another, IncW is another SVE specific instruction. It will increment the value of x4 by the number of words, that's what the W means, number of words that you can fit in your register, whatever that is. So if the partner implemented a wider register, x4 will go up by more than this specific situation, which is, as I said before, 16. So second iteration, the condition will still be true up to x4 plus 4, because now x4 is the x4's value is 16, so we'll go up to true through these 4 elements. This is going to be the last 4 elements, and everything else is going to go to false. And this is how we avoid dealing with tails. This is going to happen. It's not a problem. We just operate on these 4 elements, still vector operations, and we don't have to care about this memory. So again, the first element is still true. So we'll jump here, load one, the other, store, increment x4, and go back to the while operation. This time, because x4 starts at 32, everything is going to be false. In particular, the first element is going to be false. So when you ask branch if the first is true, it won't. We're done, finished. And if you stop and think, as I was saying, it doesn't matter how long these vectors are. If they're shorter or longer, this code will remain the same. So this is the whole idea behind vector length agnostic vectorization. If you want to see more details about SVE programming with SVE, see what new instructions we've included of all those fancy ones I mentioned before. Here's a link to the whole extension. You also can find here a small tutorial. This is easy to follow. You can follow it in about an hour or so. They go over the main things, this thing I just described here, but also how to vectorize with conditionals inside your loop. Also, there is an example about vectorization with first faulting registers. It's easy to follow. You don't have to be an expert. It's very well explained. I thoroughly recommend this one if you want to learn how to work with SVE at that level of detail. If you don't want to work with assembly, that's perfectly fine. You don't want to do that anyway. You can use intrinsics. I think the intrinsics are included in at least all major compilers, they are still probably pending to be accepted in LLVM, but they will be there eventually. And if you want some examples with intrinsics, we have these. This is also an introduction to SVE, but while this one is a generic vector or vectorization introduction, this one is more specifically directed towards machine learning. Tools to use for this: all your major compilers support auto-vectorization. So SVE, as I said before, it was designed thinking about automatic vectorization. So even though I showed you all of this handmade vectorization, ideally, all of these will work automatically and for free in these compilers. So definitely the example I just showed you, any compiler will vectorize that automatically and generate the proper SVE code. You don't have to worry about that.
Javier?
Yes.
This is Fabrizio.
Yeah.
Well, is there any specific compiler option to activate the vectorization, and how can I check that the vectorization has actually happened?
Good question. So ARM's compiler, and I think Fujitsu's at least, I haven't used the Cray one for SVE yet. Those two will vectorize automatically. So if you set the proper optimization flag, like if you do like that, no, obviously no, everything is an optimization flag. I mean, if you do -02 and above, it will vectorize. For GCC, you still have to specify the -F3 vectorize option to vectorize. So it works like automatic vectorization for any other vector extension. If you've ever used GCC to vectorize code for Intel, it's the same option for ARM. I will send you the specifics. Don't worry.
Awesome. And to check that a loop or whatever has been vectorized, I have to go inside the assembly code.
Yes, sorry, I forgot about that. Yes, that's the way I do it. I think there is a way to, there are some information flags that you can activate, at least, I think in GCC, probably also in Clang, that will warn you when a loop has been vectorized. It will tell you this, a loop in this specific line has been vectorized. If not, you can check the assembly generated. If you see Z registers, so this, because the instructions are the same. I don't know if you noticed, but it's just loads, normal loads. But you know this is a vector load because it has this Z register here. Also, the predicate Z register kind of gives it away, but for many other instructions, it's going to be the Z. If it's operating with Z registers, those are SVE registers. So at least that's how nowadays, that's how I do it. There's also in the ARM compiler, we have this software. It's called what is it? I don't remember. It's something like Code Advisor. So Code Advisor, if you run it on your code, it will not only tell you when it vectorized, but it will also tell you when it didn't and why it didn't vectorize. It's an interesting tool. I didn't write anything in these slides, in this slide deck about it. But if you're not an expert, and on second thought, I should have probably put something there because you are exactly the audience for this tool. It will actually tell you I couldn't vectorize this code because, for instance, if we go back to the source code here, a second, it shouldn't take long. There you go. If you notice this restrict keyword, this is telling the compiler that this memory is not overlapping with this memory. If you don't put that there and you try to automatically vectorize this, it won't do it because it's risky. It can break something. Code Advisor will tell you, I didn't vectorize this loop because this memory region is not guaranteed to not overlap with these two. And it will suggest you, maybe you can put a restrict here, and then I can vectorize that loop. So that's something you might want to look into it. And if I recall correctly, that's included in the basic ARM compiler, ARM HPC compiler. Does that answer your question?
Yes, thanks a lot.
Okay. So, who is implementing this? Well, I think a couple of weeks ago, ARM made public our Zeus processors we're going to sell with SVE. I'm not sure about the details, how many of those details are public, so I won't get into it. But the most famous implementation is Fujitsu. They already released some prototypes to their trusted partners, and I think they are planning on starting selling them by the end of this year. And these are the features included in this processor. So it's based on ARM V8.2. The length of the vectors is going to be like 512 bits, and it has this interesting architecture. Every A64FX chip is going to include like 4 clusters of 12 plus 1 core. Even though all the cores are the same, one of them in each cluster is dedicated to assist in the computation. It's going to be handling all the, let's say, if these 12 cores are going to be accelerating your workloads, the 13th core is going to be handling everything else effectively. Each of these clusters is going to be connected to a single 8 gigabit HBM2 memory, and then Fujitsu included this special interconnect of theirs. The Tofu interconnect is a 6D torus. It can get up to 28 gigabits per second, 2 lanes 10 ports. It's the published numbers. They're very promising. Over 2.7 teraflops, a memory bandwidth of 1 terabyte effectively per second. And now you might be wondering that, okay, I want one of those. I want to run my SVE codes. The problem is this doesn't exist, or exists, but it's not for sale yet. So the next best thing we can do is using some sort of simulation environment. And here's where I will explain a little bit what's Gem5 and what do we do when we want to test these newer architectures, but we don't have access to them. So what is Gem5? Well, more than a simulator, even though we sell it as a simulator, we market it as a simulator, it really is more of a simulation infrastructure. You can use Gem5 to build simulators. It's thought of as a research tool. This is the best way we have to evaluate new ideas, test microarchitectural changes, find bottlenecks, those sort of things, when you don't have the hardware, obviously. Gem5 offers several components already modeled, like different CPUs, interconnects, memory subsystems, some devices. All you need to do basic simulation and a bit more. Also, Gem5 will model the interaction between all these components. Here's another link you might want to check about system modeling in Gem5. There's an in-depth tutorial that goes over everything, maybe even more than you really need if you are not an architecture explorer, which I assume or is my understanding you're not. You're mostly scientists. But there it is if you want to dig a bit deeper into it.
Javier?
Yes?
A very stupid question. Is Gem5 running on, let's say, a non-ARM architecture? I mean, can I install it on x86 on my laptop?
Yes, yeah. So it's simulating an architecture, and you can simulate it from any other architecture if you want. There is one exception, though. if you want to do a really fast simulation, there is a special newer mode that I don't explain here, but you can run the CPU in KVM and simulate everything else. In that case, you do need to be running everything on the same architecture. If you're going to run KVM, if you want to simulate an x86 processor, you'll have to do it on an x86 machine. If you want to simulate an ARM processor, you will have to do it in an ARM machine. Other than that, you can do cross simulation. It's actually a common practice, and we do that every day. So
awesome. And the final question: is it for free, or should I pay?
This is open source.
Okay, cool.
This is open source software. So you have access to the full source code, some sample configurations. The most problematic thing, in my opinion, and this is a disclaimer, this is my opinion, is documentation. It's not great. The best way to learn about Gem5 simulation is actually attending one of the Gem5 simulation workshops that ARM sponsors here and there throughout the year. But those are like several hours long, and there's a lot of hands-on testing. So the simulation model in Gem5, we have three basic components. The sim objects, which are the elements that will simulate functionality, so to speak, and then master and slave ports that will be used to communicate between components. Conceptually, Gem5 is a Python library implemented in C++. And then what you can do is, from Python, connect all these components together to build a system that will be simulated. And the simulation itself, it will be run in native code in C++ simulators are slow enough without running them in an interpreted environment. The parameters of your sim objects are exposed as Python attributes, so it's very easy to configure. If you have a cache sim object and you want to change the size, you will have something like object.size. You change that, and you just instantiated a wider, bigger cache. So the execution is controlled for Python, but the implementation, as I was saying, runs in C++. The whole process is a two-step process. Is one step, you configure your system in Python, and then in the second step, from Python, you drive the execution of your simulation. The simulation is run as in a standard discrete event timing, and the time in Gem5 we measure is in ticks. Usually, I think we run 1,000 ticks. Well, we don't run them, but because this is event-driven, you don't go through every single possible step, just the ones that make sense. But I think the basic simulation is about 1,000 ticks per clock cycle, and then you can decide what your clock cycle is going to be, and timing will be derived from that. And this is the simulation workflow. You have in your Python world, this is Python script, where you will create your Python sim objects. You will connect them together. Then you can call to M5 instantiate to instantiate your whole system in C++ as well. This will be mirroring your objects in Python. And then you can start the simulation. Your objects will communicate with each other, time, so on and so forth, until something happens in your guest code here that triggers a pause in the simulation that will bring you back to the Python world, and then you can do another step of simulation, maybe change something, and just keep going. This is usually if you're doing something like sim points or fast forwarding, this is how you do it. You will use first step to run through the things you don't want to simulate without any details, and then you run with more detail second step, and so on and so forth. This is just so you have a general idea of the simulation process as it is. Main thing is you have to configure a system in Python, and then the simulation will be run in a more performant environment. So also generally speaking, this is going to be more or less your system. You will have a CPU-like element that is going to be driving the simulation. This is going to be generating the events that will trigger all the other events. I write CPU-like because it can be a CPU model, but you can potentially also use effectively a trace replay. If you generate an execution trace from your program, instead of simulating all your instructions again, if you don't care about the specifics of the CPU, you only care about the behavior of your memory devices, bus devices, or whatever, or even all the other parts of the system, you can just put here a trace simulator. You will skip all the CPU simulation and get statistics for all the other parts of the system. Once you start your simulation, you have several options. This will determine the accuracy of your simulation, the speed of your simulation, so on and so forth. We have 3 basic simulation modes. The first one is timing simulation. This will calculate an accurate, will give you accurate timing information. All the events triggered by the different devices will be queued, delayed, and sorted, so everything happens in order within your system, and you get the most accurate timing possible. Nevertheless, it's extremely slow. It's about 1 order of magnitude slower than functional simulation or atomic simulation, and that one is already like 3 orders of magnitude slower than real time. So you have to take that into account. Simulating a couple of seconds in timing simulation, it's very extremely slow. It will take hours. On the other end of the spectrum, you have your atomic simulation, where there is limited or no timing information at all. All the requests are processed instantaneously. So the moment the CPU triggers or makes a load request to the memory subsystem, it will go through all the memory subsystem all the way up to the data you're asking for, and it will retrieve it immediately. So it will run very fast, but it's not very realistic. We usually use this mode when we want to do something like fast forwarding. If you want to run a huge workload, but you're only interested in a small part, you can fast forward all the start of your workload. Then once you get to the interesting part, you can pause the simulation, switch to a different model, a timing model, and keep simulating. And the last timing model is functional modeling. This one includes some more timing information, but still the requests are processed in order as they come. They will go as deep as they have to go in your system to get your response and come back. This one is important because I/O devices are usually simulated as functional devices. You don't care about the timing of your I/O, I mean your hard drive, so to speak. You just want to get it back. Also, if you want to connect a debugger to your host or your guest code, I guess, you will need to use this functional mode to do that, because you don't want to simulate your debugger as well. You want that to run as quickly as possible. An important distinction is that functional can coexist with both atomic and timing elements, but timing and atomic, they cannot coexist. So you either run with timing and functional elements or with atomic and functional elements. This is basically it. Now, next step is what happens with your operating system. When you run your program will have system calls. It will have to do libraries, some interprocessor communication if it's parallelized, somehow task parallelism. What happens with those threads? How are they scheduled? Well, unsurprisingly, you have 2 options here. You can either simulate the operating system or you can emulate the operating system. And Gem5 offers both options. So if you want to simulate your operating system, this is what we call full system simulation. In this mode, you will have to boot a whole operating system. You have to create a Linux image with all your libraries and all your things there. And it will actually run Linux on top of bare hardware. So you have to include all the devices you need to simulate your workload. That includes keyboards, UARTs, plenty of all those things. You will also need to simulate interrupts, exceptions, and fault handlers. You can simulate privileged instructions, which is something you cannot do if you are emulating. And the most important thing to take into account here is that you're running a bigger and therefore slower model. You have to include a lot of stuff in your model system to be able to run full system emulation. Configuring full system simulation, it's quite cumbersome. So there will be some slides in the slide deck where they go through the basics of this. But if you want to run workloads in full system simulation, and you might want to if you're running things like OpenMP, for instance, because even though you can simulate pthreads, we still are having some problems with OpenMP. Eventually, it will work, and there are people who have it working, but well, I think I digress. The other option is emulating the operating system, and this mode is called syscall emulation. Here you can run an individual application, so you will have your executable. You can also have a set of applications that are running in different processors. What we do here, we just model the system calls. We bypass all your application system calls from the simulated environment to the host OS, or we will do something smart to make it believe that everything is working, or if it doesn't need to do anything, it will just ignore it. The address translation here is very simplified. You won't have to deal with page walks and those things that usually impact performance quite a lot. So as you can imagine, this model will be faster, but it will also be less accurate. Still, in many situations, especially in HPC, where applications run in user mode most of the time, like 99.99% of the time, it's fine, but just these small asterisks. If you want to use Gem5 prerequisites, you can use OS X, you can use Linux. There is some limited support for Windows 10 if you install the Linux environment, and then you have several dependencies. The basics is Git, Python 2.7, which is how you configure your systems, compiler, GCC or Clang, Swig, although I think we're switching to a new interfacing system with Python, but that should work for now. And then these three building systems. Optionally, you might want to use the DTC. This is the device tree compiler. You will need this if you want to simulate something in full system. This is why I was saying that it gets a bit cumbersome, because if you modify your system, in ARM, we don't have a hardware detection system. Everything has to be predefined in this device tree that tells the operating system kernel what's where, and there's actually no way around this, because the thing with ARM is that again, partners will implement their own systems, so you can have a generic detection system. This is the best second option, and you will have to deal with that if you want to do your own full system thing. You might want to use a cross compiler as well if you're running on x86, but you don't want to switch to an ARM machine to compile. You can just use a cross compiler, that's fine. Protobuf is, I think it's a Google tool that standardizes traces and the replay of traces. So if you want to do things as like what I was mentioning before, of instead of using a CPU, just use a trace player. You will need Protobuf. And then if you happen to have this installed, Python PyDot, when you run your simulation, Gem5 will generate a beautiful PDF with your system in block diagram of your system. If you want to download and compile Gem5. This is the repository, just clone, pull to update it. Important, the development repository. Don't try to go for stable versions or anything like that. That's going to give you more problems than solutions. So avoid that, go to development. It's stable enough. You shouldn't, it shouldn't be too painful to work on development. Things are tested and should work as they are in development. And they will actually work better than if you go to past stable. I think they gave up on the stable thing. The last one, it was like in 2015, 2014, something like that. If you want to build your Gem5, we'll use scones. This is the line. The J4 is just telling scones that it can run 4 jobs in parallel to compile. And these 2 things, these are the key elements in your compilation. This will tell scones which architecture has to compile. In this case, we're compiling a Gem5 simulator of ARM architectures. This is the guest architecture again. The most commons you will see is like null if you want to do trace-driven simulation, and x86 as well. Beware of the timing behavior with x86. We'll get into that later, but there is the fair warning. And the second part is the .opt. It can be opt, but it can also be .debug or .fast. If you want no optimizations in your code, you use debug. This is usually useful if you want to debug Gem5 itself. And then if everything is working and you don't want to modify anything about your basic system arrangement, you can compile the fast version. It takes more time to compile, but then it will run faster. If you want to use it for in syscall emulation mode, for instance, okay, I have 5 minutes left. I will have to accelerate a little bit. Once you have your Gem5 compiled, it will take as an input a script. This is the main input of your Gem5. It will execute this to configure your system. This is one example that you can find in the source code. It's not the best example if you want to learn how to configure a syscall emulator, syscall emulation system. It's better if you go to this one down here in Configs Learning Gem5 Part 1. This is much simpler because the thing with this one is that it gives you parameters to configure an extremely wide variety of systems beyond the point of usefulness. So it's quite obscure, so to speak. But it's very useful if you want to do a quick run like this. You just decide that you want 4 CPUs, you want to add caches and a second level cache. This is the memory type we want to use, DDR4, 2 GB. And then this is one of the important parameters, the CPU type. We are going to use a Derive 03 CPU. This is an out-of-order processor. That's already modeled there. You can use it as it is. It runs in timing mode. So that's how you decide what kind of simulation you want to do. And then this is another option that will accept a binary, the binary you want to run, and the options for that binary. All these options, so from there to there, are options for this script, not for Gem5. So this script is the one that's understanding this. If you use another script, don't be surprised if these options don't work. Okay, I think that's the gist of it. Once you run this, you will get your output in a directory. By default, it's going to be M5 out. You can change that, passing parameters to Gem5. And within there, you will see a
sorry, Carlo from Cineca. The binary should be compiled for the target architecture, or it is disassembled?
No, it's a binary for your target architecture. So
okay.
In this case, this thing, binary, should be an ARM 64 binary. Okay? And fair warning as well, if you're running syscall emulation, the binary has to be statically linked. Because you don't have like a dynamic library loader, because that's part of the operating system, it won't be there. The results you will see will look a bit like this. So you can see like your basics, like what was the last tick in your simulation, what was the host rate, like the simulation frequency in ticks per second. So as I was saying, like 1,000 ticks is one cycle. So if you do the math, you will see that this is like 1 gigahertz, which is the default in Gem5. It will tell you how many instructions were simulated, how many operations, including micro operations. So these should be slightly bigger than that. Well, it depends on the architecture, right? Well, these are microarchitecture specific things. They will also give you a translation of how many seconds were simulated, not how long it took the simulation, but how many seconds were simulated. This was a few seconds, and it managed to simulate like 18 millionths of a second. So that's how slow it is. And again, the number of ticks simulated, which is obviously related to all of this. But if you go down the file, you will see things more interesting things. For instance, within your system, you can see your memory controllers. And from your memory controller, you can get this statistic, the bandwidth read total. So you can read what's the bandwidth usage in that program in bytes per second. You can see something more specific, like for instance, of all your read instructions, which one, or yeah, from all your load operations, how many were due to CPU 0 instruction accesses. That's the sort of detail you can go. It's very low, really low level detail of all these things. And finally, just the main warning. What are the opportunities and limitations of simulators? There are good practices and pitfalls, right? What can you do? Or let's start with what you shouldn't be doing. If you're trying to get accurate timing numbers, you have to take into account that Gem5 is not simulating a specific x86 or ARM processor. Gem5 is simulating a Gem5 processor that runs that ISA. So timing is not going to be necessarily related to actual execution time. For instance, the CPU I was simulating is a 7-stage out of order CPU, but if you go to the real stuff, you will see things overdosing stages. So obviously, it's going to be some parallels, but it's not going to be extremely accurate. Also, if you want to draw conclusions about how a specific subsystem is behaving, you have to make sure that that specific subsystem is properly modeled. So if you want to see how your cache behaves, make sure that you have the proper replacement policy set up in your cache, that your memory is actually the real memory that you want to run. Don't run these simple memory simulators, or don't run DDR3 if you want to test HBM, those sort of things. Also, if you see something like it's out of the ordinary, like these numbers are extremely good, I'm doing great, like way more than I was expecting, or this is not working at all, not even close, what's going on? It's probably because there's something missing or misconfigured somewhere. So those words of caution. And then things you can actually get out of this is if you have everything properly configured, and anything that can have a meaningful impact in your simulation is being modeled. For instance, you want to have an idea of your bandwidth consumption, make sure that everything in your memory system is arranged as it is in your real system. Then you can trust what's coming out of that with asterisks and air quotes. It's going to be more of a ballpark thing than an accurate thing. So that's why relative information is more valuable. So if you have your memory system properly modeled and you make a change and you see that there's some improvement there, you can at least extrapolate that you can expect some improvement in the real system. But even the amount of improvement, it will depend. It can be very accurate. It can be a bit off. Also, simulations are very, very useful when you want to test the limits of your algorithm. For instance, if you want to see what would happen if I have infinite bandwidth, you can configure your system with infinite bandwidth, and then you can see how the other parts, like compute or I/O, are actually limiting your program or your simulation. Also, fortunately for people who don't want to deal with this sort of system configuration, we do have some vendor-provided simulators. I think a couple of days ago, Riken announced that you can have access to their simulator. They claim that it's within 10% of the actual numbers of the A64FX. The only caveat with this is that you cannot still publish numbers, not until the actual hardware is released, but you can start working with that. If you ask for access, they will give it to you. So I don't think there's much more I can say about that. If you have any more questions, I don't have a lot of time. I overdid it a bit. But if you have more questions, I'll be happy to answer them.
This is Fabrizio. If we have any problems, can we drop an email to you?
Oh yeah, sure. Obviously, yes, yeah.
And you are javier.setoain@arm.com.
Exactly. Yes.
Okay.
Yeah.
Well, just a very stupid question. In your experience, how difficult is to simulate, for example, a DGEM for a guy coming from basically zero?
It should be more or less this. So if you want to simulate your DGEM, you just compile it statically for your target architecture, in this case ARM, and then you can do like a basic configuration. I wouldn't even bother doing anything smarter than that. Well, let me rephrase that. If you just want to run it, this is how I would do it. I wouldn't even run the rival 3 thing. I didn't include any SVE options here, but you can also configure the vector length, for instance, and see how it behaves when it changes vector length. Running or execution time, again, if you're going to run something like a timing order for the CPU, it's going to be slow. If you have, I didn't put any numbers here, but I think the approximation was if your CPU can do 3 million of instructions per second, in timing mode, Gem5 will do about 0.1 million. So that's like 4 orders of magnitude slower. Does that answer the question?
Discomforting, but yes.
Yeah, well, this is the limitation. In a couple of days, you'll have another one of these with, I think it's Miguel, who will talk about ArmIE, which is not a simulator, it's an emulator. So if you just want to run SVE loads just to see that how they run, or to confirm that you can run them, that's much faster. It's not extremely fast, but it's much faster. You can run significantly bigger workloads with that. You just won't get all the nice statistics about bandwidth, instruction, well, some instruction proportions you can get, but not the fine details about, well, effectively the simulated parts. Is that better?
We'll see on Thursday.
I think it's Thursday, yes.
Yeah.
I believe in here, in this URL, this one, developed ARM, the research enablement kit, you also have information about ArmIE. It's relatively easy to set up, and it's trivial to run. My point being that if you want to run SVE workloads this afternoon, well, it's a bit late there, but it takes like half an hour. Any other questions? In any case, if you have any more questions, feel free to reach out to me. Or any other one in my team will be happy to help you. I hope this was useful to you, that I didn't mumble too much and I didn't digress a lot. Thank you everyone for attending, and well, see you all in the next meeting, I guess.
Okay, thanks a lot. Bye.
Thank you very much. Bye.